So if Joe challenged us with regards to the science interface to policy, I'll try to challenge us as peers and friends and colleagues in the room on what does the Anthropocene mean for the scientific challenges on water resources research and, moreover, the knowledge interface to development. And we saw the film earlier of the Anthropocene. The only thing I'd like to add is that the reminder that this is quite recent scientific evidence. The first time the idea is put on the table in an Ambio papers in 2002, led by the Nobel Prize laureate Paul Crutzen. It is actually summed up through evidence in 2004 in the eminent synthesis by IGBP, and James Savitsky is here with us. It's not until 2007 that it's really starting to get into the scientific domain. You might ask yourself, who is it that decides what's on the posters in high schools in our geological classes? Well, of course, it's the Royal Society in the UK that decides the geological eras we're in. And right now there is a geological committee working to ask itself, should we change from the Holocene to the Anthropocene? So this is recent evidence, and it has profound implications. It's not more than a year back that business starts understanding that we are entering a whole new epoch of human pressures where we are a quasi-geological force of change. The British weekly The Economist, which I have great respect for, has this wonderful, well, to begin with, on the front page, welcoming humanity to the Anthropocene in May 2011. And then it has this wonderful British understatement of how science feels in its editorial, saying that when the real world is changing faster than theory stipulates it should, a certain amount of nervousness is a reasonable response. And I think that is what will be reflected in this summary. When I talk to my students, I try to make them aware that when it comes to water resources research, we simply have to start navigating a 369 world. We are in the main climate science moving towards a 3-degree warming. We are in the 6th mass extinction of species, the first caused by another species. And we are committed more or less to 9 billion people. Moreover, as Joe reminded us, not a world with a minority having the large riches, but we're moving towards 4, 5, 6 billion people with a purchasing power of an average European. We are truly on a biosphere shaped by humanity, and therefore we're in the driving seat of change. Now, the reason why we can talk of the Anthropocene is a quadruple squeeze. It is the pressure of humanity, which has the dilemma not only of numbers, but of wealth. It is a climate crisis, which is our disturbance of the atmospheric system. But the trick is that you would have wished that this crisis or disturbance of the energy system, of the atmospheric energy system, would occur on a resilient planet able to buffer and deal with these disturbances. But as the Millennium Ecosystem Assessment showed, no time in history, as in the past 50 years, have we undermined the regulatory ability of ecosystems on Earth as during the past 50 years. So we have a double challenge of an ecosystem challenge right at the moment of a global climate challenge, which all have interface with freshwater. The playing field for humanity, moreover, is reduced by the fact that we're learning more and more that the Earth system response is not linear. It's not as if we're just taking out natural resources and incrementally things change in a linear and predictable way. Instead, long periods of incremental change can swap abruptly and often irreversibly when systems from lakes to rainforests to savannas tip over thresholds and change state, when feedback directions shift. This reduces the space for human development. We all know in this room, of course, that freshwater is a driving factor behind all these four, a key to development, a key for the stability of the climate system. It's behind all ecosystem functions and services, and it regulates the stability of resilience and landscapes. But at the same time, freshwater is the #1 victim of change. Clearly, if mitigation of climate change is about gases, adaptation is generally about freshwater. The evidence behind the Anthropocene is empirical, and we've all seen the hockey stick patterns. Here in draft form, we're coming out with a book on water in the Anthropocene, launch at the World Water Week later this year, with an update which we're doing with the IGBP on the left-hand side of the drivers of human change, everything from population to consumption. On the right-hand side, you can pick any parameter that matters in the Earth system for human well-being. They look the same, everything from deforestation, air pollution, climate change, loss of biodiversity. We're picking key factors from the freshwater system, and you recognize these curves. They look roughly the same. In the past 50 years, we have a very rapid increase in everything from withdrawals of fresh water to water quality deterioration. And we're starting to see a frequency increase, an amplitude increase of natural hazards, as Joe pointed out. This is the great acceleration of the human enterprise, and it looks like this. So this is the drama, that you can pick essentially any parameter in the Earth system that matters for human well-being. Up until the mid-1950s, we had more or less a relatively limited impact at the Earth system scale. We're 3 billion people 10 years after the Second World War, and this is where we put in the high gear. The great acceleration of the human enterprise starts, and we move up to the point at the top of these exponential curves. And it's only interestingly, over the past 20 years or so, that we start to realize that this model doesn't work. Meaning that up until perhaps 1989, 1990, the conventional growth model of pushing environmental impacts into the global commons actually worked. The Earth system was very forgiving and didn't send invoices back to the subsidy the Earth system thereby provided to our wealth creation, which has been phenomenal, by the way, as we all are aware. But it's over the last 2 decades that we're starting to see indications of nonlinear feedbacks with major costs to the economy. The unprecedented drought in Texas 2012 pulls down the US GDP with 1%. Similarly, 12 years of drought in Australia, forest fires and floods in India and Pakistan, etc. The frequency really paying back into the economy. So it's a recent development, which is really critical for us to be aware of as well, because often we're accused of saying that you've been warning for decades and decades. Well, that's not true. The empirical evidence is here now, and we're the first generation to have this empirical evidence on our table. So science is stepping up to this knowledge, and this is just a set of examples of synthesis from science to communicate to world leaders that we have entered not only a new era, we're starting to reach what we can call a saturation point. We're hitting the ceiling, or approaching the ceiling of hardwired processes at the Earth system scale. And the State of the Planet Declaration, for example, from the global environmental change community is one example of such a very critical communication with regards to the new juncture that we're facing. Joe went through Future Earth very much in detail here. I would argue that this is science stepping up to its own evidence. It's 30 years of fantastic advancements in Earth system science now being transformed into a mobilization of integrated research to better understand risks, but also to find solutions in a global transformation to sustainability. Well, the risk patterns are so well known in this room, and just running through a few of the evidence pieces here. I mean, one is the evidence from the ensemble of climate models that we cannot any longer exclude very dramatic shifts in rainfall patterns, seasonality, onset of rainy seasons across the world, with the hardest impacts often in the most vulnerable regions. Water scarcity is a tremendous challenge. In the lower right-hand corner, we estimate that we need to increase freshwater use in food production from our current 7,000, including rain-fed and irrigated agriculture, to at least 9,000 cubic kilometers per year to feed a world population of 9 billion people, with the regions in red here showing regions that simply do not have neither, at least today, indications of freshwater resources, land, nor economic resources to meet those growing demands. So clearly a potential destabilizing factor in the world. You've probably seen this very important paper in my mind from Glenn Peters and colleagues showing that from the AR4 IPCC scenarios, you recognize the A1 scenarios, which takes us to 4.2 to 5 degrees warming, the blue curves, the A1 family with a safe 2-degree future, and the fact that we're following in black dots the 4.2 to 5 degree worst case scenario of the IPCC, which when it was launched in 2007 was criticized for being an exaggeration of a worst case scenario that could not happen. And on the right-hand side, Potsdam Institute colleagues showing that we might be coming close to a point where the feedbacks in the Earth system could self-accelerate warming, and we could come to a point of a runaway situation where freshwater drives much of those changes. You may have seen these NASA data, which I think is a phenomenally important empirical evidence coming just half a year ago, showing weather observations from 1950 until today with the occurrence of +3 sigma extreme events, meaning that where are the places on Earth where you have occurrences of extreme events, all of them water-related, droughts, floods, heat waves, which are occurrences that should occur less than 1 in 1,000 years. And the drama is that just 50 years back, this essentially did not occur on planet Earth, 1% of the surface. And today we see 13, 14, 15% of the Earth's surface subject to these kind of changes. So this is occurring on a planet that has increased its temperature with roughly 0.8%. So this is, I think, the ultimate evidence that we can no longer separate global environmental change from occurrence of stochastic high-risk events in the current world we're living in. Kumi and colleagues from Finland have shown this, I think, very good synthesis of the social side of the water challenge, which is the same period, 100 years of development, with roughly 3.5 billion people suffering from various degrees of water scarcity in our world today, half of the world population. Now, this is a drama in itself, but look at the dotted lines, which is the exponential growth of success. This is our engineering efforts of trying to solve this problem. This is 5,000 cubic kilometers of fresh water dammed in our rivers. This is groundwater extraction, irrigation systems, pumping of fresh water, chasing our own tail to solve this problem. So we have a collision of two great giants, in my mind. One is the social challenge of a world that still has unfinished business, moving towards 9 billion people, on an Earth system where fresh water no longer can be expected to be stable, as we've always perceived and always assumed in the past. We have this tremendous food challenge, shown not least from the Ag assessment that we need to increase food production in the world with 50 to 70% just in 40 years to feed a world of 9 billion people. And many estimates show, and this is one of the analysis, that we need another 2,000 cubic kilometers of fresh water, roughly, just to meet the Millennium Development Goals of halving hunger. 2,000 cubic kilometers of consumptive freshwater use, as you all know, is the same amount, roughly, as we are consuming today, so a doubling. We have recently estimated that in this future, even if we're able to increase yields and productivity, we would have roughly 4.1 plus 1.5, roughly half of the world's population in regions suffering from water scarcity, even if we have a positive trajectory for agricultural development. So truly a fundamental challenge. But what does all this mean then to combine the Anthropocene, which is really about pressures, and the rising risks of thresholds? Because I would argue that the key insight for us in our future science agenda on water is to combine these two, the pressures and the response of the Earth system. And the trick is then, as I've mentioned, that we're starting to see more and more evidence that ecosystems, the biosphere at large, does not necessarily react to changes in conditions as the upper left-hand corner suggests in a linear way, but rather with thresholds and even hysteresis. We define this as resilience in 3 dimensions. One is the ability of a system, from a rainforest or a lake system or the Arctic ice, to persist disturbances without tipping over into an undesired state, but also the ability to adapt, and in a situation of crisis, what's the ability of a social ecological system to transform in a new development direction. So a broad array of science on what role does water play to build adaptive capacity, robustness, and transformative capacity. So what's the evidence that we need to take tipping points seriously? Well, here's one, and I've taken this because personally I would argue this may be the most important graph we have today on Earth, because it shows for the first time a shift in feedback direction at the big biome scale. This is data from NASA. It's compiled by Jason Box and colleagues at the Barrett Institute, and you may have seen it. This is days of the year, and what it shows is in the y-axis is albedo. It's the reflectivity of incoming solar heat reflecting back to space from the Greenland ice sheet. And in colored lines, you see the predictable pattern that we wish to have, a roughly 90% return of incoming heat from Greenland. The black line is the drama of 2012. For the first time in observed history, the entire Greenland ice sheet is melting. And just a shift in color means that albedo goes through the floor. The feedback goes from cooling to warming. And just those 2 weeks of entire melting has been calculated to be equivalent of over 300 exajoules of energy. Now, 300 exajoules of energy is more than the annual consumption of energy in the US. So momentarily, Denmark goes past China and the US as the largest climate-forcing nation on Earth, when the Earth system changes direction of feedbacks. And of course, this is the scientific nightmare, but it's also the study of thresholds, understanding what are the feedbacks that keeps a system in a desired versus an undesired state. We have examples of water-induced tipping points in different systems. We're now mapping these for different systems on Earth, so water seems to play a role in terms of regulating stability in everything from rainforests to savannas to large lake systems. I think we need to understand these potential water-induced tipping points much more profoundly. Tony Barnowski and colleagues and many others ecologists have shown that biodiversity plays a role in keeping systems, from marine systems to terrestrial systems, in a stable state. And we all know that freshwater is behind all biodiversity. Regional biomes like this system here, this is the 75% loss of rainforest in Borneo, which of course has always been studied rightly as a tremendous challenge in terms of indigenous community livelihoods and biodiversity, but increasingly showing that when we lose rainforest to a certain extent combined with climate change, we may have a tipping point with, for example, a dieback of rainforests flipping over to savanna states, influencing regional rainfall patterns and thereby the economy. We have the work by Huub Savinay and colleagues at TU Delft, and colleagues probably here also in the room, showing that we've probably underestimated moisture feedback from forests, and in regions in red here is modeling research showing regions that depend to more than 80% on neighboring countries' green water flows from forests. A geopolitical bomb, not least, but also showing again the interdependence between nations and biomes on Earth. So what does all this mean for a unified framework for world development within a safe operating space on Earth? Well, to begin with, it requires from us to back up one step and ask ourselves the question, well, if we are a geological force at the planetary scale, if we're in the Anthropocene, what is the desired state of the Earth system to support a world of 7, soon to be 9 billion people? I would argue we have an answer to that question, which is coming from fantastic ice core data in the upper right-hand corner, showing the last 100,000 years of life on Earth, shown with a proxy as temperature variability, in this case from Greenland. We've been modern humans for 160,000 years, so we've had the same ability to develop civilizations during the entire period here. And as we all know, it was a jumpy ride. We were hunters and gatherers. We had a rough time, in and out of tremendously variable freshwater conditions, until we enter the extraordinarily stable Eden's Garden, the Holocene, which has a ±1 degree Celsius variability, which determines the onset and offset of all growing seasons on Earth and freshwater supply in our hydrographs. And this is the Holocene, and this is the period when we invent agriculture, and this is the period when we develop modern civilizations as we know it. So the answer, in a way, as a challenge for science and policy, is as dramatic as it's simple. The Holocene appears to be the only equilibrium of planet Earth that we know that can support the modern world as we know it. And if this is the case, it simplifies life quite substantially because we know the Holocene fairly well. We know the geochemical flows, we know the settlements of the different biomes, and we can then ask ourselves the question, what are the Earth system processes we need to be stewards of to maintain Holocene-like conditions? Which resulted in the planetary boundary framework, which you may have run across, which basically just answers this question. What are the processes we need to be stewards of to establish a safe operating space in the Anthropocene, shown here in green? And I won't go through this in detail, just to say it's not only climate change, and certainly science indicates that freshwater is one of the regulating processes for the stability of the Earth system. And we estimated in this 2009 publication that we still have some degrees of freedom on freshwater use globally. We landed in a boundary definition of 4,000 cubic kilometers of consumptive freshwater use. We're now working on an update for this work and downscaling this to river basin scale. We've been criticized for probably being too conservative, that in fact we have indications that we've pushed the water boundary too far in many regions of the world. But this provides a challenge for science in terms of how do we relate to the fact that things have to now add up at the planetary scale. Now we've been trying to connect this to the Sustainable Development Goals process by asking ourselves the question, is there a unified framework for sustainable development in the Anthropocene where we connect global sustainability and Earth system criteria in the outer blue ring here with development, basically saying, have we come to a point where we now have to recognize that if we're not in a point of limits to growth, at least we are in a situation where we need growth and development within Earth system limits, that the Millennium Development Goals need to be achieved within scientifically defined Earth system boundaries. And this, of course, can be debated, and I think it would be nice to do that at this conference. We suggested in a Nature commentary led by David Griggs and colleagues that yes, we would want to see a freshwater sustainable development goals, but it should be integrated across the economy, society, and the Earth system. So integrated goals across science, environment, social, and economic parameters. Now, in my just 2-3 remaining minutes, let me just challenge in terms of what would this then potentially imply for a safe future for humanity? Well, clearly we need a set of transformations, from a global energy transition for a safe climate future, a food security transition, an urban transition, a biodiversity management transition, and all of these require fresh water as a backbone. We've estimated, led by John Foley and colleagues, that we can feed the world through a sustainable intensification of agriculture. And the question then is, what paradigm would this mean for water resilience if one takes these transitions seriously? And I'll just take the example of fresh water. Now, we therefore would suggest that we need to consider a new conceptual framework linking global change with management of resilience at the local scale, which adds a new component of sustaining rainfall. And that this then kind of connects to the traditional agenda of water supply, food production, water for ecosystems, but also the larger cross-scale challenge of rainfall management, done in a green-blue context of sustaining water for both ecosystems and society, recognizing that one of the untapped potentials is really to understand freshwater availability, not only from the blue water perspective, but also the tremendous availability of fresh water, which is green, shown not least in the comprehensive assessment already in 2007. In green here, the countries supplying food from rain-fed agriculture. Now, the solutions, therefore, can be varied in terms of intensification. I would argue there is an opportunity in the interface between rain-fed and irrigated agriculture, that this requires what we've called a triply green revolution, which is all about intensifying in a sustainable way, using water more effectively, as Joe pointed out. We're now exploring in Ethiopia, for example, what we've called a triply green revolution of building resilience through water intensifying irrigation systems and small-scale rain-fed systems, with returning sanitation through productive sanitation systems, with new forms of land management, like, for example, conservation tillage. And that this has a lot of evidence. I mean, we can take Gates Foundation-supported projects, work going on around the world on productive sanitation, all of it adding up to evidence that these things can actually go to scale. The CGIAR is mobilizing, as you may know, in something called the Waterland Ecosystem Project, a $70 million per year endeavor for a green revolution combining new thinking on water and land. So the conclusion overall is profoundly challenging for development and science, that global sustainability has now become a prerequisite for human development across all scales, which is a human journey, which is clearly something that needs to be connected down to the community scale. And then my message is, so to say, to inspire hope and challenge this conference is that maintaining Holocene-like conditions in the Anthropocene is humanity's grand challenge. And that this development needs to now occur within a safe operating space of Earth's life support systems. Water plays a key role in enabling that transition across all sectors, from energy, food, health, transport, urban development, consumption, and that an integrated approach that addresses resilience, both from the persistency thresholds, adaptive and transformative capacities required for prosperity, and we don't have the answers for this. So science has an enormous role to play in the near future. Thank you very much.